Good afternoon, everyone, and welcome to this SMRI webinar. My name is Sean Mardo, and I'm the Factory Support Manager at the SMRI. So today's webinar will be hosted or presented by Steve Davis, who's the R&D Manager at the SMRI. You will all know Steve very well, of course. Hi, Steve. Steve today is presenting on final molasses boil down test that we perform at the SMRI and its relation to the target purity difference formula that we all know very well. But I think more than that, he'll also be presenting on molasses losses and even allude to best practices that we can employ to reduce those losses. And I think that's quite important, and I think that's one of the reasons why this webinar seems to be already very well attended, is because I can just share a trend for you very quickly. So what you will be looking at currently are the trends of molasses losses. So that's sucrose lost to molasses in South Africa and pallets lost to molasses in Southern Africa over the last 20 years. And what you can see in both South Africa and Southern Africa is that there's an increasing trend with regards to molasses losses. And if you go one step further and if you look at the molasses losses at each factory, you will see that there are opportunities in every single one of the SMRI member mills in South and Southern Africa to reduce losses to molasses. So Steve, with that as a background, I'm now going to hand over to you to take us through the presentation and give us some tips on how we can actually reduce those molasses losses. Steve.
Thanks, Sean. Good afternoon, everybody, and thanks for joining. I have pre-recorded this webinar to make sure I say the right things I want to say. So we're going to play through the webinar. I think it's probably about 30 minutes, and after that there'll be ample time for questions and discussions. Okay, if you have any questions along the way, feel free to put them into the chat, and then we can deal with them at the end. Okay, so here goes.
Good day, everyone. My name is Steve Davis. I'm the Research and Development Manager at the Sugar Milling Research Institute. Today I'm going to be talking to you about the fine molasses boil and target purity. Now, target purity difference is a key parameter in measuring the performance of the factories. But how many people understand what it means and how to interpret it? So I'm hoping by the end of this little talk, you have a much better feeling for what it's all about. So the main aim of the back end of a raw sugar mill is to exhaust the C molasses to the lowest possible purity in order to recover the maximum of sucrose. However, of impurities in the limits the amount of sucrose that we crystallize. High level tends to exhaustion. In other words, it tends to keep the sucrose. Whereas reducing sugars, fructose and glucose, higher levels of those tend to aid exhaustion. In other words, they almost co-crystallize the sucrose out. However, the overall non-sucrose content is more important than a high reducing sugar ash ratio, as we'll see later on. I'll give you some examples. Because the higher the non-sucrose load, the more molasses is made and the more sucrose is lost. And in this talk, when I talk about non-sucrose, I refer to a difference between bricks and sucrose percent. Obviously, if you are using poll in the factory, you will refer to a non-poll loading instead of a non-sucrose loading. But the principles are more or less the same. So if we just have a look at the back end of our sugar factory, and this I adapted from Dave Love and Dave Mazel's SAS paper of 2009. I'll be coming back to it again because it illustrates it very clearly what is happening. So here we have mixed juice that has been weighed, sampled, and analyzed coming into the factory. And in that mixed juice, there's sucrose, fructose, glucose, ash, and various other types of non-sucrose, gums, polysaccharides, all kinds of things. And essentially what we're trying to do is we're trying to recover the maximum amount of sucrose into raw sugar. And we want minimum amount of sucrose to go to fine molasses. And we want a minimum amount of fructose, glucose, ash, and other non-sucrose into raw sugar. So essentially, we want sucrose to go that way, everything else to go that way. And so the final molasses purity is basically the ratio of the amount of sucrose in the molasses divided by the sum of sucrose, fructose, glucose, ash, and other. In other words, that makes up the bricks. So, as I mentioned, the higher the non-sucrose loading, the more sucrose will be lost to molasses. And this is purely a consequence of the need to maintain a standard sugar purity. So we can use the well-known SJM formula to calculate the recovery of sucrose to sugar as a function of sucrose purity, juice purity, and molasses purity. Now remember, this is a simple mass balance and represents the best possible recovery you can get, theoretical recovery, and it assumes no losses. So you can't do any better than the SJM, you can only do worse. And so if we now look at an example where the molasses purity is, say, 35%, we can see that the juice purity has a big influence on the theoretical recovery. So if you have a juice purity of 85, we can expect a theoretical recovery of 90% of the sucrose going to sugar. However, if that juice to 65, then our recovery drops to 2. So that's it completely in the absence of any other losses. That is simply because you now got a larger non-sucrose load. Therefore, you have to create more molasses to get that non-sucrose out. That obviously takes with it a whole lot of extra sucrose. However, when the juice purity is that poor, it is quite likely that your molasses purity is not going to be even as good as that. And let's say it goes up to 40%. In this case, you can see our SJM recovery drops down to 65%. So for a juice purity of 65 and molasses purity of 40, you are not going to be able to get any more than 65% recovery of sucrose into your sugar. Everything else is going to leave into molasses, no matter how well you operate the back end of your factory. Love and Mazel also came up with the so-called 3 laws of molasses loss, which are good guidelines for how to limit your losses. So the first law says that the quantity of non-sucrose and fine molasses must be minimized, because at any given purity, each unit of non-sucrose will take with it 100, so P over 100 minus P units of sucrose. That's essentially what we've seen in the previous slide. So you want to minimize non-sucrose and fine molasses. Second law, the achievable fine molasses purity or target purity must be kept as low as possible, except where this would contradict the first law. Now, we look at, again, an example just now, as to say how we can, in fact, get a very low target purity, but in fact, we're doing that at risk of contradicting the first law. And the third law is the actual fine molasses purity must be reduced to as close to target purity as possible, or even better below, except where this would contradict the first or second law. When we're looking at molasses exhaustion, we need to distinguish between a rate limitation and an equilibrium limitation. So remember, at the the low purity end of the factory, the viscosities are very high and things happen rather slowly. So a rate limitation means that the exhaustion is not complete by the time the masquerade is cured, because crystallization is slow at low purities, low temperature, and high viscosity. But if you left it for longer, more would crystallize out. By contrast, equilibrium limitation means that the impurities in the molasses are limiting the lowest purity that can be achieved. So no matter how long you leave it, it's not going to get any lower than that equilibrium purity. And so the so-called molasses boil down test determines the equilibrium purity, which is the best a factory could possibly do. How do we do this? So to determine the equilibrium purity, we get a sample of molasses, and we boil that molasses sample down to between 86 and 88% dry solids under vacuum in this apparatus shown here. We use dry solids because it's more accurate than bricks at low purities. Essentially, molasses goes in here, it's fed in slowly through a pipe, it's got a steam jacket, and it's under vacuum, and there's a stirrer in here. And so we gradually evaporate the water and collect the condensate in here so we can estimate what the dry solids is. And so once we've filled up the vessel here with molasses and it's reached the dry solids, we're ready for the next step. The chamber is then removed and we add caster sugar as seed. And so this is to create a large surface area to allow the supersaturated sucrose on. Obviously, because of the very sticky nature, the high viscosities, you know, the rate of migration of the sucrose molecules through the masquerade, the molasses, is very slow. So you need to provide a large surface area to minimize the amount of movement that has to take place for crystallization. We then bolt it onto this crystallizer and we cool it down to 40 degrees over 72 hours with stirring. And at that point, it has then reached equilibrium. So in other words, these molasses is then saturated. All the supersaturation has been removed by crystallization. After that, we extract a sample of mother liquor through the fine screen. Here you can see the fine screen in the bottom of the vessel. And that retains all the crystals, so this is essentially the same as a Nooch sample. We then analyze the feed molasses and mother liquor for FGS and ash, and we plot the equilibrium true purity, which is sucrose over dry solids, versus fructose plus glucose over ash in the feed molasses. And then for many tests, we can determine the regression line to predict the target purity from the fructose to glucose to ash ratio. So remember, the analysis of the Nooch molasses here is the equilibrium purity. So a whole lot of work was done on many. So to develop the target purity formula, over many years, a whole lot of molasses boil down tests were done using a wide range of samples, and the results are shown here. So for any given point, basically we're showing what is the equilibrium purity plotted against the fructose glucose ash ratio of that sample. And originally the black line was the logarithmic target purity difference, but in 1995 Ian Smith proposed an exponential formula given here, which better fitted the predictions at the extreme ends, particularly with very low reducing sugar levels, i.e. down this end. So from all of these data points, you can then draw this regression, and for the exponential expression that Ian Smith used, you can see the correlation coefficient is 0.835. So it's quite good, but it's certainly far from being perfect. And again, there's quite a range of scatter in these points. What we must also understand, though, when we look at the data more closely, is that certain mills behave quite differently to others. So, for example, for mill A, has a cluster of points here. So those the molasses samples from that mill consistently gave a higher equilibrium purity than predicted by the target purity formula at the same reducing sugar ash ratio. So the workers were unable to exhaust those molasses samples down to what the target purity formula predicted. By contrast, in mill B, the equilibrium purities were consistently lower than predicted by the target purity formula for the same reducing sugar ash ratio. And this is simply part of the nature of the molasses and so on. And therefore, it's very important to understand what your own factory's typical TPD values might be. And we'll come back to this again later as to how you'd find that out. There's even an odd sample here where the equilibrium purity was a whole 4 units higher than the predicted target purity at that reducing sugar ash ratio. So it's not an error. It simply is that molasses was quite abnormal and could not be exhausted very, very well. But it was still at equilibrium purity here. So if we look at all of this, what's important to realize with that scatter, that there is an uncertainty of plus or minus 1.9 units in the target purity prediction. So that's the uncertainty you have. When you're looking at your actual molasses TPD, remember that there's an uncertainty in your molasses analysis, but there's also an uncertainty in the target purity prediction of plus or minus 1.9 units. So you certainly can't quote a TPD to more accurate than about 2 units, I would suggest. So the TPD, the target purity difference, is the difference between the actual molasses, true purity, and the target purity predicted from the formula using the fructose glucose to ash ratio in the original molasses. Now, this is determined by the SMRI on weekly composite molasses samples and is reported in the weekly mixed juice molasses reports. Because obviously the factories themselves, until recently, did not have the equipment to determine fructose, glucose, ash, and then sucrose on a routine basis. So the good benchmark is that good factory operations can typically achieve a best TPD of 2 units. But you need to be aware of differences between typical factory levels, as shown on the previous slide. And there is a factory in South Africa that consistently was running at TPDs of about 0 units, simply because their molasses could exhaust very, very well. If we look at the South African industry target purity difference trends over the last 20 or so years, and what I've done here is I've plotted the lowest value in the industry per mill, the average for the industry, and the highest mill value. So you can see here in the sort of mid-2000s, again, this is the factor I was talking about, it was consistently getting a TPD of about close to 0. But that gradually crept over time, and more recently was achieving sort of 2 or even 3 units. You can also see that the industry average has definitely been increasing over time as well. And so this is a lost opportunity, because that's additional sucrose that's going to molasses that we should theoretically be able to recover. So this is the target purity difference. So there is a difference between your actual molasses and the target purity. So you should be able to maintain that. If we look at the highest, you can see there's some scary values here, running about 10, but some of these are with back-end refineries, which has an additional complication of recycling ash back to the raw house. And then this one here was an abnormal year when one particular factory is performing very poorly. Anyway, the point I'm trying to make is that the trends are not good. There's increasing trends on the highest, lowest, and the average, and it's something that we need to try to reverse, because this is relatively quick wins. And hopefully by the end of this talk, you might have a better understanding of things we can do about it. Right. The target purity difference is also calculated using a mixed juice reducing sugar ash ratio. In other words, we analyze the mixed juice reducing sugar ash and calculate what is the molasses target purity based on that. Now, the difference between this and the TPD calculated on the molasses reducing sugar ash ratio indicates the effect of non-sucrose creation in the factory back end. And most likely is a changing in reducing sugars, and ash levels are less likely to change. So let's just think this through carefully, step by step, and what the implications are. So we have our mixed juice coming in with a certain reducing sugar ash ratio. Okay, if we have inversion taking place after the mixed juice sampling point, inversion will lead to the reducing sugar ash ratio increasing from mixed juice to molasses. So we're saying the ash levels are fairly constant, but now reducing sugars are going to go up. Because the reducing sugar ash ratio increases, the target purity decreases from mixed juice to molasses. So the target purity predicted from the molasses reducing sugar ash ratio is lower than that predicted from the mixed juice reducing sugar ash ratio. And therefore, the target purity difference based on molasses is higher than the target purity difference based on mixed juice for the same molasses purity. So in other words, because you've created extra reducing sugars through inversion, your target purity difference is higher in molasses than you'd expect from mixed juice. Ideally, the difference should be less than 0.5 units. But if it's much more than that, then you suspect that you might be getting some inversion in the back end of the factory. Purity, and I've called this the fallacy. So people will say, well, okay, well, if we have got some inversion, we're going to be lowering the target purity, and therefore at a constant target purity difference, the molasses purity will also go down, and therefore we must be better off with the lower molasses purity. However, this inversion is increasing the non-sucrose load, and that leads to increasing sucrose loss to molasses, as I pointed out in one of the early diagrams. So let's just take a hypothetical example, but using sort of reasonably real numbers to illustrate how this happens. So let's take a mixed juice purity of 87.97%, a sugar purity of 99.5, and molasses target purity difference of 3.9 units. And we assume this is constant because that's determined by how you operate your crystallizers, your mass speed reheaters, and your centrifuges. So assume we can keep those consistent so the target purity difference doesn't change. So the parameters we're going to look at here are the molasses reducing sugar ash ratio, molasses target purity, molasses actual purity, the non-sucrose loading as percent on sucrose in molasses. So this is tons non-sucrose divided by tons sucrose in mixed juice times 100. And sucrose lost to molasses as a percentage of sucrose in mixed juice. Then finally, boiling house recovery. So for normal operation, we got these typical values. The sugar ash ratio is 0.62, the target purity 36.64, molasses purity 40.53, and the non-sucrose loading worked out to be 7.2%. Sucrose loss to molasses is 9% of sucrose in mixed juice, and the boiling house recovery is 91%. But let's now assume that things are going badly, and we've got 5% sucrose inversion evaporators. What does this mean? Well, with that inversion of sucrose to fructose and glucose, it pushes the reducing sugar ash ratio up to 1.54. And of course, that means then that the molasses target purity will go down to 31.18. And so the constant TPD means our molasses purity is now 35.07. So you can say, oh, hooray, we're actually doing better because our molasses purity is lower. However, because of that inversion, our non-sucrose loading has increased from 7.2 to 11.9% on sucrose and mixed juice. Okay, so it's quite a substantial increase. And the sucrose loss to molasses has jumped from 9 to 13.9%. And remember, it's because basically all of the non-sucrose has to go out in the molasses. So the more non-sucrose you have, the more molasses you make, and therefore the more sucrose you're going to carry with it. At the end of the day, the consequence is that your boiling house recovery drops from 91 to 86, which is big, lost money. So to summarize, inversion, it looks like you're doing well because the molasses purity is lower, but because the quantity has gone up, you're actually losing out big time in the sucrose loss to molasses. And that is even excluding the direct loss of sucrose because of inversion. So there's an additional 5% sucrose that is no longer available to go to sugar. So it is all around bad news. That's why inversion is a real enemy of the process manager. So if we go back to our first our molasses laws, so where things go wrong here is that this issue here fails the first law. In other words, we have increased the amount of non-sucrose. So that contradicts the first law. The second one is this molasses target purity. So the second law says you must keep the molasses target purity as low as possible, but not by contradicting the first law. So we've only been able to get low molasses purity by contradicting the first law by making more non-sucrose. So all round, this fails both first and second laws of molasses loss. Other things we can look at to understand what may be happening in the factory is things like the non-sucrose ratio. So the non-sucrose ratio is defined as tons of non-sucrose and sugar plus tons of non-sucrose and molasses divided by tons of non-sucrose and mixed juice. So basically saying we've got so many tons of non-sucrose and mixed juice in, and we've got so many tons of non-sucrose out. And what is that ratio? So if non-sucrose is neither created nor destroyed, and we haven't lost anything, then we expect that non-sucrose ratio to be 1. So this is based on the assumption all the non-sucrose and mixed juice must end up in final molasses and sugar. So if the non-sucrose ratio is greater than 1, it means that non-sucrose is being made in the factory, i.e. between mixed juice and sugar and molasses. And this is usually because of sucrose inversion. If the non-sucrose ratio is less than 1, it's less usual, but it is possible. And it can be due to massing or analysis errors. If you're underweighing your molasses, obviously it'll give you an incorrect low value here. It can be physical loss of low purity streams, or it can be the result of destruction of fructose and or glucose. So all of these things need to be investigated if you've got odd ratios. We can also calculate the fructose and glucose ratios in a similar manner to the non-sucrose ratio. But we can ignore the fructose and glucose in sugar. As I said, it's very, very small by comparison to what's in molasses. And then we can look at the ratios. If the fructose ratio and the glucose ratio are both greater than 1, then inversion is happening. In other words, there's more fructose and there's more glucose coming out than going in to the factory. If the fructose ratio is about 1 and the glucose ratio is less than 1, then you may be getting maillard reaction happening in the back ends. Particularly at high temperatures, low purities, the glucose tends to degrade more rapidly with the maillard reaction. So this is bad news because it creates acids and it creates color and it can lead to foaming. So if you've got a fructose ratio of about 1, glucose ratio a lot less than 1, maillard reaction is a problem. By contrast, if your fructose ratio is less than 1 and the glucose ratio is about 1, then you may be getting fructose destruction in the evaporators, because fructose is more readily destroyed at high pH and high temperature. So, for example, if you're over liming in your clarifier and in your first effective evaporator, there's a good chance you may be getting some fructose destruction. So, it's a good idea to monitor these ratios in your factory, get to know what the typical values are, and then get to understand what causes them to go up or down, and particularly when they're out of line with your expectations. Another factor we can consider to understand what's happening in terms of sucrose loss to molasses is the so-called molasses factor. The molasses factor is defined as the tons of sucrose in fine molasses over the tons of non-sucrose in mixed juice. So basically, we're saying we know for every unit of non-sucrose in mixed juice, we're going to lose so much sucrose in fine molasses. But what we see over the course of a number of seasons is that this ratio has been climbing steadily and steadily and steadily. And essentially, again, this comes back to more likely inversion in the back end, because if you had no inversion, then the amount of sucrose loss in fine molasses shouldn't really change if your TPDs were constant. But because you're getting inversion, then you're obviously creating more non-sucrose and you're losing more sucrose to molasses. So again, this is a worrying trend, and you need to keep an eye on it. So this brings me back to the TPD and the boil down test. So assume your factory is running quite nicely, all is looking well, and you send your weekly sample of molasses off to the SMRI for analysis, and it comes back and it says you've got a TPD of 12 units. And you look at this and say, no, that can't be right. You know, let's go and check. We're doing everything right as far as we know. You know, the mass heat is not too hot. We don't have any leaks in the crystallizers. Our wash water in the centrifuge is fine. The screens are fine. But why is the TPD so high? Could it be that the molasses is unusual molasses? That something happened to it? Oh, okay. Let's find out. So remember that the TPD is the difference between the actual molasses purity and the predicted target purity based on reducing sugar ash ratio, assuming that the target purity represents the equilibrium purity. So now we're saying, well, maybe it doesn't. So let's ask the SMRI to determine an equilibrium purity. So then you need to supply us with 1 kilogram sample of molasses and give us about 2 to 3 weeks for the test of analysis. And then you'll get a whole set of results that looks something like this. So the sample login, the BD means is the sample for boil down, molasses sample, the mill, the date, and the serial number. And so for the molasses as received, we'll analyze the fructose, glucose, sucrose, sulfated ash, and dry solids. You'll also get a result that says BD. So this is the molasses after boil down to check that we've reached the right dry solids. As another block is BD Nutch. So this is now the Nutch molasses after equilibrium. And here we determine fructose, glucose, sucrose, dry solids. And then finally, the calculation box. So how do you interpret this? What does this all mean? Is this good or is this bad? Okay, so let's piece it together bit by bit. So sucrose over dried solids in the original molasses sample gives you your molasses true purity. In this case, 42.17. Fructose plus glucose over sulfated ash will give you the reducing sugar ash ratio. In this case, 0.77. For the boiled down molasses that's exhausted to the nutch and then nutched, the sucrose to dry solids ratio, the true purity, gives us 35.59. Okay, so that is now the equilibrium purity. Then, using the reducing sugar ash ratio, we can calculate the molasses target purity, and it's 35.49. The molasses true purity minus the target purity then gives you actual molasses TPD. In this case, it's 6.68 units. Okay, so it's not good, but it's not outrageous. It's maybe higher than you'd want it to be. Okay, so finally, does this tell us that the molasses is strange or not? The last thing is we subtract from the nutch true purity, molasses target purity. So this is the nutch TPD. So this is the difference between the actual equilibrium purity and the target purity predicted by the formula. And in this case, the value is 0.1. What does that mean? That means that, in fact, for this sample of molasses, the target purity formula is predicting the equilibrium purity pretty well, because that difference is very small. So it means that there is nothing abnormal about the sample of molasses, that a high TPD is a result of operational factors in your factory. You cannot blame strange molasses for having a TPD of 6.68. So just be aware of that. It may not give you the answer that you want, but it will certainly give you an answer. So what impacts the mill's TPD in the C station? First of all, C masquerade bricks. The higher the bricks, the better the exhaustion, but obviously too high bricks will impede curing in the C centrifuges, and such simply doesn't flow. So there is a practical limit. High viscosity masquerades, especially in the presence of gums, this affects the rate, but not the equilibrium purity. In other words, the crystallization is slower, but if given enough time, it'll still reach equilibrium. We know that viscosities can be reduced by increasing the temperatures, but the trouble is that will also increase the sucrose solubility, so you're actually not winning. Poor cooling or insufficient residence time in the C crystallizers, obviously. And your C crystal size distribution is a big issue. A wide crystal size distribution range hinders molasses purging. In other words, the molasses can't easily flow through a mixed grain on the centrifuge. Presence of small crystals, they'll pass through the screens into the molasses, or else just dissolve readily, so that sucrose is lost to molasses that you can't recover. And elongated crystals or needle grain from the presence of kestoses also impact on purging and lead to difficulties. Then obviously things like overwashing in C centrifuges is simply going to dissolve a crystal, and torn or worn C centrifuge screens will lead to crystal going into the molasses and obviously increase your TPD. And obviously, and also things like abnormal ash compositions. So for example, high sodium levels can also impact the TPD. But if we have a look, that for all of those items in blue, if you did a molasses boil down test, you will find that the target purity would be fairly close to the equilibrium purity. In other words, it would show there's nothing abnormal about the molasses. Whereas for the abnormal ash composition, you might well see that the target purity is predicted is quite different to the actual equilibrium purity achieved. So let's have a look at a couple of these impurities. I did a whole lot of work in the mid-2000s with Barbara Scrooney to look at the effect of, some of the polysaccharides on exhaustion. And we spiked a whole lot of molasses samples of various types of polysaccharides here, as you see, and then did the exhaustion and calculated the equilibrium minus the target purity. And as you can see, there's generally no sort of correlation. So, for example, if you look at the total values here, as the total polysaccharide content goes up as it increases from left to right, we're not seeing a definite increase in equilibrium minus target purity. Again, because the gums tend to limit the rate of exhaustion, not the actual equilibrium value. So yeah, gums are a nuisance, but the effect is on increasing viscosity and lowering the rate. If we look at ash composition, and here's some work that Prem Sarvay did in 1998, and then he took some samples of molasses and spiked subsamples with various levels of sodium, potassium, and calcium chloride, and then boiled down, determine the equilibrium purity versus fructose glucose to ash ratio. So obviously, the more of these salts he added, obviously the fructose glucose ash ratio goes down. But you can see here that the equilibrium purity went up quite dramatically when they were spiked with calcium and sodium compared with potassium, which basically suggests that if you've got high concentrations of sodium or calcium, that your equilibrium purity is going to be much higher for the same total ash compared to if you had largely potassium present. So it could well be that if you're getting very high equilibrium purities, much higher than target purity, that you do have an abnormal ash composition. Just for reference, this is where the target purity formula line actually predicts. So you can see his original molasses, already the equilibrium purity was a unit and a half above the predicted target purity. And as he spiked it with ash, with calcium and sodium, it in fact diverged even further from the target purity formula, whereas with potassium, it actually dropped below. So at very high levels here, you can see that the equilibrium purity was in fact well below what was predicted by the target purity formula. Of course, nowadays, you all have NRS instruments in your laboratory, I hope. So you can take a sample of molasses from your machine, dilute it and scan it to the NRS instrument and have a TPD value within minutes of taking the sample. So you can now do a TPD for each centrifuge once a shift to identify problems, instead of waiting for the weekly composite result, which is not terribly helpful. However, remember that the NRS analysis does not predict equilibrium purity, only the TPD. You still need a boil-down test for that. However, with the ability to do individual machines at high frequency, if one machine gives a high TPD and others are normal, then it can be a machine problem. So, for example, if you look at these set of results here, it's clear that machine number 4 is giving a much higher TPD value and the higher purity rise than the other machines. So we need to have a look at what that reason is. And just from this, possibly the bricks is a little low. Are we overwashing in that machine? So the NRS allows us to get a far better handle on what's actually happening in near real time and solve the problems there and then, and not wait for the end of the week. So, what are the take-home messages? TPD is a valuable measurement for assessing C-station performance, but many factors affect TPD. We need to understand the influence of each to help with diagnosis, from cane quality through clarification to all boiling house operations. Typical values vary between factories, months, and seasons, so you need to become familiar with the trends in your factory. and react to abnormal situations or rising trends. Most requests for boiled down tests of the SMRI revealed nothing unusual about factory molasses behavior. Some did confirm high equilibrium purities relative to target purity, I agree, but they were the exception. So I hope you have found this of value. For further reading, I recommend you look at these SASTA papers, which give you much more detail on the stuff that I've talked about. But I'll be happy to answer any questions.
Thank you very much, Steve, for those pearls of wisdom that you shared with us. I see the webinar is actually quite well attended, so if any one of you missed any of those pearls of wisdom, you're welcome to have a look at the presentation, which I'll upload onto the website shortly. Steve, to let you know that some of the references that you used, we have the authors in our audience, so we've got the likes of Prem Sahadio and Dave Love in the audience. And I encourage those authors to share their thoughts on molasses losses and how we can actually go around reducing those losses. Steve, there's no questions as yet, so we'll give our audience a bit of time to actually post their questions or raise their hands. But in the meantime, maybe I can ask you a question about molasses losses. And I think factory staff will want to know whether those losses are as a result of quality that's processed or whether it's as a result of factory operations. Is there a way in which we can tell where those losses are actually originating from? And in saying that, I'm obviously alluding to the likes of the CRB formula. If you can please comment on that and its application for sugar millers.
Oh yes, obviously the intention of developing the CRB formula was to try to calculate or estimate a boiling house recovery that is independent of mixed juice quality. In other words, it eliminates the impact of cane quality. So that is one way you can look at it. If your cane quality is varying, if you calculate the CRB, it'll tell you whether your factory operations are still consistent. But other than that, generally you need to, as I said, look at your non-sucrose ratios, fructose and glucose ratios, and so on, and just try to understand whether you're creating any non-sucrose in the back end, which is bad news. That's the first indication. Then simple things like looking at purity rise and purity drops across the back end with nutches. What is your purity rise on curing across your C centrifuges? It should be maybe sort of 2-3 units. If you're getting a purity rise of 5 or 6, you definitely got a problem there. Either overwashing or torn screens or so on. So there's a whole lot of the various things that one can look at, but there's no sort of magic spell that you can just wave your wand and it tells you the answer. You actually need to understand all these factory figures and where they derive from and how they work, and then how to interpret them in relation to what you're seeing in your factory itself. And that generally takes quite a few years of experience, some hard learned lessons as well to really get to grips with these issues.
Sure. Thanks for that, Steve. There is a question from Chiaba from Tonga Tulet, and he wants to know about the implications of reducing the C centrifuge screen size to avoid loss of crystal in molasses.
Yes, good question. Obviously, as I said, that loss of fine crystal through the screens is a source of sucrose loss to molasses. And one could say, well, maybe we should make this drop size smaller. the difficulty with that is that it reduces the open area of the screens through which the molasses has to drain. So basically, by making a finer screen size, you're reducing the molasses purging rate, and so what in effect is happening is that you may reduce the amount of sucrose lost to molasses, but you end up recycling a whole lot of that non-sucrose back with the C sugar all the way back to your A boilings. So you increase the recirculation load of non-sucrose in your factory, which is a bad idea from many points. So that is why over the years, the factories have settled on the typical screen sizes we use now as the best compromise between the two opposing effects.
Yeah, thanks for that, Steve. I think you touched on the key point there about non-sucrose return to the row house, which will obviously limit cane throughput initially, lead to even greater molasses and increased viscosities on top of that. So it's a definite no-no. There's a question from Ashvir from the Ilovo head office, and he says, thank you, Steve, for an excellent presentation. What would be the recommended course of action for when a boil down test is done and the results indicate a Nooch TPD of, say, greater than 3 to 4 units, which we know to be the sort of benchmark that we use for TPD?
Yeah, thanks, Ashvir. An interesting question. What we would then suggest is to have that sample of molasses analyzed in more detail. In other words, do a detailed ash composition, to analyze for the various cations and anions. So I mentioned sort of the typical ones: sodium, potassium, calcium, magnesium, and then sort of the chlorides and sulfate, and compare those results with other ones we have to say, is there an abnormality in terms of the ash composition? So as I indicated from Prem's work, it can have quite a major influence. And then that would then say, yes, because the ash composition is out of line with the typical ones from which the target purity formula was developed, we can understand that the Nooch TPD might be high. And also we've seen this, for example, with back-end refineries, where they're recycling sort of jet 4 to the raw house, which has quite different reducing sugar ash ratios to those found in the raw house. So obviously it does skew the answers. And in some cases, we have found that was the reason for the high Nooch TPD. We also have been asked in these kind of cases, is it because of gums? Is it because of dextran? Is it because of starch? And again, what one can analyze for those things, say, well, are they abnormal levels? But as I hope I indicated quite clearly, the effect of those polysaccharides is in fact to reduce the crystallization rates, and because of the increased viscosity and everything else, and they don't have a huge influence on the equilibrium purity. So remember that the big issue is that a factory is operating continuously. You don't have infinite amount of time to allow everything to reach equilibrium. So certainly when your viscosities are high, it's full of gums and everything like that. You don't have the time to allow the stuff to reach equilibrium. So you will see a high TPD, but I would suspect that your Nooch TPD wouldn't be particularly abnormal. So the short answer to your question is, yes, you then want to analyze the molasses for a whole lot of constituents just to see what may be abnormal in that molasses sample.
Thanks, Steve. Steve, maybe if you can also just comment on CSGs and maybe even crystal elongation in relation to Ashvir's question on TPD being greater than 3 to 4 units.
Again, the effect on crystal elongation is one of, well, there's two effects. One is the reduces the crystallization rate, because essentially you've got less surface area, and also it hinders purging in the centrifuge, because you've got this needle grain and often breakage. But at the end of the day, your Nutsch TPD will suggest that molasses is typical. You may have a high TPD, but your Nutsch TPD says that you have the target purity is predicting equilibrium purity fairly well. So that's why it's very important to understand the impact of the rate versus the actual equilibrium values. I hope that answers your question.
Thanks, Steve. Steve, there's a question / comment from Gavin Smith, RCL. And he says, well done. With sugar imports to a back-end refinery, I guess it is more difficult to look at non-sucrose ratio and mixed juice TPD as indicators.
Yeah, Gavin, absolutely. So one thing you could do there, for example, is to look at your mixed juice TPD, but then look at take the samples of APAN feed and determine reducing sugar ash ratio on that. And what is your TPD based on APAN feed, which then obviously indicates all your returns. And that might give you an idea of what the difference in that TPD is because of the returns coming in. Certainly understand that when you're sort of doing toll refining and importing a large amount of raw sugar from elsewhere, the recycling of that non-sucrose is a lot more than you would have if you were only refining your factory's own raws. So yeah, I would say then you take other samples and then compare before and after addition of those returns and see what the calculated impact might be.
Sure. So, Steve, there is a question that I'm going to ask, and maybe somebody from the audience can maybe comment on it, because it will depend on many factors. And that question is from Obinya, who asks, what's the recommended screen size for C-centrifuge machines? Because he doesn't want to recycle molasses, of course, and he doesn't want to lose any sugar crystals, of course, as well. So we'll leave maybe for somebody from the audience to pick up on that one. There's a comment from Santosh of API Solutions saying that, not a question, but just an observation, there are very few, if any, C-station centrifugals that have water flow meters. Steve, I know this is a particular pain point of yours.
Yeah.
In many instances, water is turned on without much consideration for its quantity required for the type of masquerade that's being processed. So I don't know whether you can maybe just briefly comment on some of the centrifuge work that the SMRI is performing and your observations with regards to the lack of water flow meters and what that means.
Yeah, I mean, yeah, thanks, Sean. So part of some of the work that we're doing, and hopefully all many of you have heard of the Sugar Factory 4.0 project that we're running. And a couple of them are looking at monitoring molasses, sugar loss to molasses, across the sea station, across the boiling house, and so also we're looking at it with our NRS decision support toolkit. What can we measure to help the operators understand what's going on? And so it's very, very much the case that, as I said, the amount of water that you add in the centrifuges is going to have a big influence on the quality of the separation. And if you're over adding water, then you're likely to be dissolving crystal into the molasses, and obviously you're losing sucrose. So yeah, in some of the work, I have been quite surprised to find out that some stations don't measure water flow rate into individual centrifuges. To me, it's just a fundamental that you should be doing. in order to optimize the process. So yeah, and obviously that would need to change according to the quality of the mass being processed, as you say, Santosh. So my recommendation is that if you don't have flow meters on, well, you should have. Otherwise, how do you know how much sucrose you're dissolving it into molasses?
Sure. Steve, there's a bit of a comment from Celo Chile, and she says that our mills are so used to controlling the processes using pole purities. Is it possible to have a seminar where you can show us the differences between pole and sucrose purities? So maybe I can just take this one and tell Celo that we actually did have a bit of a seminar around this at the beginning of 2020 when we had an NRS workshop at the SMRI, and those presentations are all uploaded on the website. But we'll certainly, it's actually a common call for us to maybe point out some of the differences between pole and sucrose as you travel through the factory, because I think industry staff will be quite used to pole sucrose ratios on C molasses. I mean, we've been reporting on that for many years. So we will have a webinar in that regard, Celo. I think it's not just the pole sucrose ratios that may be changing to the factory, but it also affects many of the parameters that we are used to having a look at as well. So we'll certainly take that into consideration. Thank you.
Yeah, sure. Thanks, sure. I just want to point out that obviously in the talk today, I've been pretty much talking about sucrose because for the very low purities at the back end of the factory, because the differences between pole and sucrose, pole doesn't give you an accurate idea of what's actually happening. So that is why, in terms of TPDs and boil downs, we actually use true sucrose and we use dry solid, as I said, instead of bricks. So it's just to make it more accurate. So when you're getting the low purities in your C station, the differences between pole purities and sucrose purities are going to be quite large. And so as Sean says, we will you can have a look and try to give some guidance as to what the expected differences might be.
Thanks, Steve. I think just wrapping up, we've been more than an hour now. There is a comment here from Dave Love, one of your references, and he says, excellent presentation, Steve. Dave suggests a reference to Alan Julian's 1985 SASTA paper regarding crystal size and purity rise over C centrifugals. It also shows a close relationship between centrifugal purity rise and TPD. So thanks for that, Dave. That particular paper will be accessible to members through our website.
Yeah, I will look that one up and I will add that to the reference list in the PowerPoint. So if people look at it later, it'll be there.
Cool. So Steve, maybe just as a parting shot, another pearl of wisdom or a few maybe from yourself with regards to why you think molasses losses have been increasing in the industry, and more importantly, what can we do about it?
Yes. I think there's lots of issues. I'm sure the factory people are well aware of it. Get back to basics, attention to detail, and understand the process, understand what impacts on your various process parameters, and make sure that you monitor and control them. So, as Santosh said, if you're not measuring your wash water into your C centrifuges, you've got no control over how much sucrose you're dissolving. So that's one of those things. So just do your regular checks so that your purity profiles are correct. Now that we have the SMRI NRS available and we have developed and rolled out our mini notch filter, it's much quicker and easier to take notch samples across the whole boiling house and look at your purity drops and purity rises on a more frequent basis and make sure that those are within the desired ranges. And then look at best practice. Refer to these various SASTA papers written by the experts. It's full of very useful nuggets of information as to how to monitor and control the process. And so, yeah, it's really just attention to detail, keep your eye on things, measure things, and understand what the impacts of the various things are.
Yeah. Steve, we've got just one last question that we'll take from Trishan. Any other questions, I think, that are posted on the chat, we'll certainly get around to it, maybe on email. So Trishan asks an interesting question. He hails from UCL factory. He also thanks you for a great presentation and says that with molasses quality that changes through the season, obviously with a change in cane quality, how often would you recommend a boil down test for mills? And he also goes on to say that this will assist mills in benchmarking acceptable molasses purities through the season.
Okay, yeah, the answer to that is that I would only suggest doing a molasses boil down test if you're getting an abnormal TPD value, which is outside your expected range. And I'm sure many of you know that I've been presenting the sort of factory performance calculations lectures for many years on the SMRI 10-week course. And those who attended that will remember that I get to the point of boring in saying you need to know your factory values, your factory trend. So what I would suggest is, you basically should be looking at your molasses TPD every single week, and also look at the TPD based on the mixed use as well as the molasses, and just trend those. And you'll see that the trends do go up and down across the season. But if the trends are out of line with what you expect, then you say, well, something odd has happened here, because it's not what we normally expect to see. And then the first thing, so, well, what might have changed? Has there been an issue with cane quality or something like that? And if you can't, then maybe say, well, yeah, we've now, our TPD was running at 4, it's now jumped up to 10, from one week to the next. Maybe there was something odd about the molasses, and that might be then identified from a molasses boil down test. But I'm not suggesting that one should do it routinely, because, as I said, in most cases, it does suggest that the target purity formula is predicting the equilibrium purity reasonably well within a couple of units, as I said. So it's more when you're getting unexpected results that are out of line with your normal trends that you said, well, let's investigate further and see what we can find.
Yeah. Steve, I think you highlighted that is the importance of getting your samples into the SMRI when we're looking at developing industry correlations, because that's going to help you to have your samples predicting better with regards to the correlations. And of course, I'm alluding to the NRS and getting samples across to the SMRI so that we can include that in our equation calibration. Yeah. Steve, we're wrapping up now. I'm just going to say again, thank you very much for those pearls of wisdoms that you've shared with us. I think it was a very, very informative presentation with certainly a lot to absorb. So if any of our more members have missed any of those important insights, they're welcome to have a look at the presentation that we'll upload onto the website. And in addition, of course, we are always available for any questions or assistance with regards to helping the mills with their performance. So on that note, thank you, Steve, and thank you all for attending. Stay well and stay safe.
Thank you all for attending.
Thank you.
Bye.
Thank you. Thank you. Thanks, well done, Steve.
Thanks, Steve. Thank you.
Thanks, Evan.